Hello, I was watching a recent debate slash discussion slash chinwag slash whatever that FTFE had with Jeranism. And at one point, Jeranism said this part right here.
So we did the east-west. All right. So sunsets in Australia versus sunsets in the north. So somebody's putting together the evidence right now. I don't have it for you right now, but I'll ask
Right.
you if we showed this evidence, what you would think of it. So I have a guy down in Australia who's filming sunsets throughout the year. So he filmed back at the our summer solstice, his winter solstice, and watched as soon as the top of the limb of the moon sets. Oops, sorry, I gotta set my clock. As soon as the top of the limb of the moon sets, then he starts calculating how long it takes until it's completely dark. Okay.
Right.
Because as you know, here in the north, what happens is in the summer, when the sun sets, we have an extended period of time of light. Maybe it's an hour and 15 minutes, hour 30. And then in our winter, we have, because this, well, I don't need to tell you where the sun is, but in our winter, that shortens. The sun sets and we only have, say, 35 to 45 minutes of light because of because of the nature of the way the sun works. Now, in Australia, we would expect then the opposite to be true, that in
Mhm.
their summer, that, right. What we're finding is it's the opposite. So in the southern summer, their sun sets and it gets dark fast, 45 minutes. In their winter, the sun sets and it gets dark in an hour and 15. So what that leads us to believe is that the outer track of the sun is longer, making the sun have to move faster. It still goes 15 degrees an hour. Nobody's contesting that. But if the sun is moving faster, it's going to cause it to get darker faster. And so if we show that, which is a tough thing to show, but I mean, he's got the evidence. You just have to probably have somebody yourself do it so that you see it's the same. What would be the possible explanation for that?
What's the time differences again?
It seems to be about an hour and 15 minutes to get complete darkness at the most, and then like 45 minutes at the least. They're just opposite of the north. So in the north here,
Yeah.
we have an hour 15 in summer, 45 in winter. But it seems like in the south, they're getting 45 minutes in the summer, an hour and 15 in the winter.
And when I heard him say that, something didn't quite make sense with what he was saying. Just for context, what I understood what he was saying was if you look at the amount of twilight, that is when the sun has just set to the point where the sky is fully black, other than the stars, and you compare the amount of twilight time between the June equinox and the December equinox in the north versus the south, I got the impression that Jeranism was trying to imply that the south is not a mirror of the north, at least not exactly. And so I reached out to FTFE the next day on Twitter and I sent out a few screenshots from timeanddate.com. For example, here would be one of them. This is for today. Rather than try to go to various places around the world to verify it for ourselves or somehow try to ask somebody else to run experiments, possibly a simpler solution would be to use a tool like timeanddate.com and pretend that it is accurate. After all, if time and date was not accurate, then people around the world would be able to go to them and say, your tool is garbage, it's not representative of reality. Therefore, I would have to assume that timeanddate.com is accurate regarding things like the amount of twilight. And with that, we can start to do a bit of an analysis. Just as a quick recap, twilight consists of three different bands of increasing light intensity, or in the case of the evening, decreasing light intensity, and is broken up into civil, nautical, and astronomical twilight. I'm not going to cover each one. It's basically there. You can do your own research and figure out what it is. The key point, however, is that each of these bands represents roughly 6 degrees of sun's altitude below horizontal. So civil twilight is going to start when the sun sets to when the sun is 6 degrees below horizon. Nautical twilight starts at 6 degrees and ends at 12 degrees below horizon. And astronomical twilight goes from 12 to 18 degrees below your horizon. And when the sun is anywhere below 18 degrees below your horizon, that means that the sun cannot illuminate the upper atmosphere either indirectly or even indirectly through Rayleigh scattering. Some time ago, when I was still working on my skywatching app, I implemented a feature that simulated that twilight. Here, the altitude of the sun is still 6 degrees above the horizon, and as time progresses, there it's 3 degrees, 2.4, 1.6, 0.8.4. Here we have just reached past sunset. For those who don't know, I did not bother accounting for refraction in this app. I didn't want to involve that part of the math. So here, what I did was I picked Sydney, Australia, because I believe that was one of the locations Jeranism brought up. And as of today, or actually yesterday for them, when I'm recording this, sun should set at around 1747. And as you can see, the light in the sky keeps getting dimmer and dimmer. And at some point, when the sky goes black, like right about there, night should have been at 7:12 p.m. and we can verify that with timeanddate.com. The sun set at 5:49 p.m. and night started at 7:12 p.m. The algorithm I use to calculate the position of the sun is from the NOAA spreadsheet calculator. I've made videos in the past and I've linked to it. So what I did was I modified the app slightly to start at noon on a given day and keep advancing the time until the sun set. In other words, when the sun just went below the horizon, and then I kept advancing until it reached 6 degrees below, marked that time, kept going, marked that time, kept going until it reached 18 degrees below the horizon. I put all the data in this spreadsheet here. I'm going to make this spreadsheet available, so check the description below. This column is the Unix timestamp. This is the date and time in Eastern Time. I chose 75 degrees west and I started from 60 degrees latitude south, incrementing every 15 degrees. So if I want to find out where Sydney is, by the way, Sydney is at 33 degrees south, not 30. So that is going to be a slight difference. Then I have to go and find... I started September 22nd, which is the autumnal equinox. So I'm going to have to go to the very end to catch up to next year. These are the 4 days in question. This is going to be Eastern Time, not the time that Sydney uses, which is that time zone. This tab consists of 4 rows for each day at a given latitude. Column F is the azimuth, column E is the altitude. So you would go 1750, 1850, that's about an hour and 24 minutes. In the time and date samples tab, I took the result for September for Sydney and I copied it here. I removed the direction from this cell so that I could subtract this one from these other ones. So from sunset to the end of civil twilight is 25 minutes. From sunset to the end of nautical twilight is 54 minutes. From sunset to the end of astronomical twilight is an hour and 23 minutes for today, according to timeanddate.com. I've done that for several locations and several times, and everything seems to match. In this case, I took these from the source data, and I took these from timeanddate.com, and then I did a bit of math, and I compared the results. And as you can see, both of them are within minutes or seconds of each other. So I would say that the algorithm I used to calculate the location of the sun and from that derive whether it was in twilight or not twilight seems to match. So what I ended up doing was I took this and I ran it through a script to subtract each of these Unix timestamps from each other so that I could get the total number of seconds for each given band of twilight. So in the sunsets parsed tab, column A is the date, B is 60 degrees south at sunset. So basically sunset starts at 0 seconds. Column C is the duration of the first twilight band, so 3033 seconds in this case, so just under an hour. This column includes the time for the first band, but also for the second. And then finally, this is the total duration of twilight. Then F through I represent 45 degrees south. J through M represent 30 degrees south. I've included all of these other columns in this tab, but we only need to focus on these here to finally address the question or the topic that Jeranism brought up. When I graphed this, I got a bit of a surprise because I was not expecting what I saw. If we start at the green plot, you can see that this local minimum is about 4,319 seconds, and there's a maximum here at the summer solstice in June at 4,724, and same thing over here, 4726 maybe. And this one, 4328, 4319, happens to be at the September equinox. Somehow I was thinking maybe the sun would spend a little bit more time at either of the two solstices rather than at the equinox. But I've been thinking about this a little bit and it kind of makes sense. So here if I'm looking due west at the equator, you can imagine that as the sun is setting, it's going to reach a point where it's 18 degrees below the horizon. You're standing inside the path of the sun as it's going around the Earth, or rather, as the Earth is rotating around the sun, that is. You're inside the plane that forms that circle, I guess that's how you would say it. And you are also standing at a location where that plane is also perpendicular to the axis of rotation. So in that case, it makes sense that the amount of twilight in that place at that time is the least. Things get a little bit trickier on the solstice because now you are no longer standing inside the plane of the sun's path in the sky. And just like having a hula hoop that you're holding off to the side, the sun's path looks a little bit curved like this. And so rather than going straight down at the equator on the equinox now, the sun is starting to curve away on the solstice. And so the sun is going to take a slightly detoured path until it reaches that 18 degrees below your horizon. And then, of course, 6 months later, the same thing happens on the other side. So it makes sense that the amount of twilight time at the equator is equal at both solstices, and that the twilight time is equal at both equinoxes when you're on the equator. And things get a little bit more interesting as you go farther north or farther south. But as you can plainly see in this graph, this blue line is 45 degrees south. It is a mirror copy of this magenta line that is at 45 degrees north. And what I also find interesting is that unlike at the equator, the local minimum for each of these is no longer at the equinox, but it's starting to shift slightly away from it. And in the case of 45 degrees north, that would be March 4th. Anyway, that's going to be it for now. Thank you for watching. If you like this video, I would certainly appreciate the thumbs up. to subscribe if you're not already subscribed, and leave a comment below. It does help the YouTube algorithm, and we have to do their work for them nowadays, it seems. And with that, I'm going to see you again in another video soon enough. So bye for now.